Welcome back to Calculus. Today's recommendation is something I'm very excited about. The movie Tremors is on Netflix right now. If you have not seen Tremors, it is one of these movies that is so bad it is fantastically good. It is about a totally, stereotyped, quote-unquote, Western town, I think in Arizona, that is attacked by giant subterranean, snake worm monsters that are completely unbelievable. The special effects are terrible, and the whole thing is acted really poorly, and it is just a total delight to watch. I highly recommend it. It's just fun and escapist. So that's my recommendation for today. Our goal now is to compute surface area of surfaces of the form z equals f of xy in R3. I'm going to try to not go extremely over on lecture today, so let's try to see how we do this. So how are we going to make a formula for surface area? So the idea here is we're going to get a little ds, which is our, surface area. This is our, differential area. And how are we going to get that? We're going to get it with cross products. So your picture for this should be that you've got some kind of, surface floating around in space. And you've zoomed in a lot. And so this is just a little patch, a little graph that you are drawing of your surface area. And you want to find, what is the little contribution if you're down here in the, okay, so here's your x, y plane underneath the z-axis, which I'm going to avoid drawing. So just think this graph is, I don't know, I guess I am going to draw it. There's the axis. The graph is somewhere above this. So this is z equals f of x comma y. And so down in the xy plane, you've got this tiny little, rectangle that's dx by dy. So that's your little dA, dx, dy, okay? And I want to know, when you graph that little rectangle up above, it's getting a little deformed, right? So, it's on the plane below, but if f is really steep, that rectangle above it, could be a lot more area, because in a small move downstairs, you're moving a lot vertically. So upstairs, it's still going to basically be a rectangle, but its image is going to look kind of like, you've got some sort of deformed little rectangle. Okay, so here's how we're gonna do this. So let's make this dx and this here dy in that direction. Then u will be my vector in the dx direction, and v will be my vector in the dy direction. And then the area of this little ds is going to be the area of that parallelogram spanned by u and v. And so that's just u cross v. Absolute value. Okay, magic use for cross products that I bet you didn't see coming. So the reason why I'm using this setup is that, in fact, v and u, we can describe them really easily. So you should imagine that if you just are moving in the x direction, so if this is your x-axis down here, and you've got this little step, which is dx, then what's happening upstairs is you're at somewhere on this surface, and you've now moved u above it. And so that's how you're supposed to be reading this left picture. This u is above the dx. And so I'm trying not to draw stuff vertically because it's just going to become immensely confusing. But this little slice of a picture is supposed to fit over here. And so u's coordinates, well, this vertical direction is my z-axis. So in fact, use coordinates as a vector in the x direction. It's going dx, because that's the width of the thing below. And in this direction, oh, that's, well, it's basically the tangent plane direction. It's a tangent line, it's a derivative, it's a partial derivative. So we'll write this as df dx dot dx. So it's kind of like the amount that f is going up as you walk in the x direction. This is how we define partial derivatives. So that means use component, its x component is dx. Its y component 0. Y is not even in this picture. It's not even moving in that direction at all. And the z direction is df dx times dx. Okay, and I know that there is a difference here between these partials and these d's, and it seems totally arbitrary. Trust me that this is the coefficient that makes this work. This should be a partial derivative, and this should be a differential. And if you want to know more about that, you're going to have to take more math classes to understand the distinction between these two terms. But this is the right one to use, technically. So, if you do the same analysis, you'll see that these coordinates are nothing in the x direction, dy in the y direction, and df dy times dy in the v direction. And then, if we do our little cross product, what you'll get is that ds is now going to be the absolute value of, and I will multiply it out for you. It's going to be fx dx dy minus fy dx dy and dx dy. Okay. Cool. So you should note that this u cross v is also a normal vector to the surface, kind of instantaneously. So this is something very similar to our little gradient function. And so there's some deep connections going on here. So what we want, though, is this absolute value. And I'm just warning you, I might have gotten my signs backwards. I might have computed v cross u instead of u cross v when I did these. And so if you got off by a negative, that's okay. We're taking an absolute value, so that's going to all disappear. So when I take that absolute value, I end up with the square root of fx squared dx dy all squared plus fy squared dx dy squared more plus dx dy squared. That looks terrible, but what we'll do is just factor out the dx dy that squared that's in all of these and move it outside of the square root. So this is totally the same as the square root of fx squared plus fy squared plus 1 dx dy. And that right there is the formula that we need to remember for surface area. It's the only remaining thing I want to draw. It's just our final answer. So surface area is going to be an integral over some region in the xy plane of ds, this form that we got. And what it'll compute is the surface area above that region R. So fx squared plus fy squared plus 1 dx dy, and that's the surface area above R on the surface z equals f of xy. So in the next video, we will use this formula to compute some surface areas.